Hello, everybody, and welcome to today's webinar. Today, we'll be looking at data center modeling in Flownex simulation environments. My name is Vincent Britz. I work as a thermal fluid solver developer at the head office of Flownex in South Africa, and I typically work in developing new components in Flownex, as well as helping out on consulting projects where we help our clients solve new problems experienced in industry. Over the last 3 years or so, I've had a lot of hands-on experience in a lot of the different data center applications that we'll be talking about today. Before we go into the detail of today's webinar, I'd just like to explain the webinar interface. On your right-hand side, there is a questions tab. At any point in the webinar, please feel free to type in a question there, and we'll answer all your questions at the end of the webinar. Okay, so our webinar today will be made up of 3 different parts. First, we'll be looking at some basic introductions to Flownex. This is to help anybody who's new to the software to understand the general use of Flownex and how it fits into simulation as a whole. Next, we'll look at some data center specific applications. And finally, we'll talk through a detailed example of a thermal ride-through simulation and show you how we would model that in Flownex, as well as some of the results that we can get out of the software. So Flownex itself is an engineering tool designed to simulate entire systems. We have a large library of components that can be used to capture the performance of each of the parts of the system. This might be components such as pumps or tanks or heat exchangers or turbines. And all of these components can be arranged together in the same way that you would organize a process flow diagram. And by connecting these components together, it's possible to understand the performance of an entire system. Flownex has a lot of advanced fluid models incorporated to capture the physics of the different fluids that are used in these systems. And these fluid models include liquid models, gas models, two-phase fluids such as refrigerants, as well as more complex models like humid air or other mixtures. Flownex has both a steady state and a transient solver, and along with our transient solver, we also have a library of control components that can be used to model both analog and digital control systems that control the entire system. This is very useful because it allows you to simulate the process itself as well as the control system to understand how the true performance of the system would be. Flownex is also able to couple with a lot of third-party software. Common applications would be couplings with some of the ANSYS software, such as Fluent or Mechanical, MATLAB and Simulink for control simulations, Excel and Python for incorporating some custom code that you've written, as well as coupling with Six Sigma, which we'll talk about later in the webinar. Flownex is developed within an ISO 9001 quality assurance environment, and the software is tested in line with nuclear standards for verification and validation. So we ensure that the software is developed at a very high quality standard. The software also has a very user-friendly interface and is quick for new users to learn and easy for people not familiar with the software to have a general understanding of what is being modeled in the system. The software also includes a detailed help manual for each and every component, and it explains the inputs and results of each component, as well as some of the background theory that went into developing the component to give users a good understanding of what the component is doing in the system. And lastly, the software, lastly, we have resellers all around the world. There are 24 resellers spread around the globe, so we're able to provide you support in your language and in your time zone. Okay, so looking at some of the data center specific applications, Flownex is used in data center modeling in a wide variety of applications. The first one that I'd like to discuss is in steady state design simulations. Flownex is particularly useful there because we can characterize the performance of many components in the system, and then the software can interpolate between the different design information that we provided to the simulation to understand how the overall system will behave. This means that it's possible to approach manufacturers and ask for, say, 5 or 10 different selections to characterize the performance of a component in the system, and then the software can interpolate between there. This essentially removes the need to approach manufacturers every time there is a small change in the design and a new sort of operating point for that component is needed. Flownex is capable of thermal ride-through and short break scenarios as well, but we'll talk about that in the next part of the simulation. Flownex is also able to assist in quantifying excursion hours. This is particularly important with some of the hot weather that the Northern Hemisphere has been experiencing lately. It's possible to take typical weather data for a region and perform an automated set of parametric runs in Flownex. This gives you an indication of what the expected chilled water temperatures are, or the expected air supply temperatures will be for different ambient temperatures, and will allow you to quantify the number of excursion hours using typical weather data. So, for example, you might take an existing data center design and try apply it in a new region. Using the software can give you a good idea as to how that design will perform under these new ambient conditions. Additionally, on top of excursion hours, it's also possible to quantify some other resource usage. The common applications here are water usage when using heat exchangers such as hybrid dryer coolers. These are often Yagi heat exchangers, for example. And when data centers are deployed in in cities with limited water available, it's often required to quantify that water usage for the correct application of permits. So Flownex is particularly useful in taking weather data and being able to use that to quantify the amount of water used in different environments. Additionally, when using ATES cooling, this is cooling using groundwater to supplement the cooling inside the data center. We can use Flownex to quantify the volume of water that will be used, as well as the temperature that we'll be injecting the water back into the ground. This is also important when it comes to applying for permits. Lastly, on the design side, Flownex is able to model the control logic in the system at a very low level. This allows us to capture the key performance of the system. And by modeling the control philosophy in detail, we can actually test different control philosophies in the system. So we could, for example, test different modes of switching pumps on and off to try and keep the pumps closer to their best efficiency point, and prototype and test that control logic in a simulation where it has no impact on the final performance of the system, but can be used to motivate design changes in your data centers to improve their energy efficiency. From an operations standpoint, Flownex can be used to assess performance changes following modifications in the system. So perhaps you have a data center with 4 data halls and you're looking to add 2 more. If you're going to be merging 2 chilled water rings and perhaps adding some new chillers to the system, Flownex can be very beneficial in this sense, where you can use the software to understand the pressure drops in the system as a whole, as well as what's going to happen to the transient performance of the system by modifying the original design. Additionally, the instrumentation in data centers is often limited to key locations. So root cause failure analysis can be performed using the software by failing specific components in a simulation and then comparing the results in the software to the results at the key locations where you have measurement data to try and understand what a component failure resulted in the actual system failure that you experienced. So moving on to the main focus of our webinar today, we'll be looking at a thermal ride-through. By a thermal ride-through, I'm specifically talking about a loss of mains power and a transfer to generator power. This is sometimes also called a short break or a mains to generator transfer. Specifically, we're looking at the change in temperature in the chilled water in the system. The reason for this is typically because major components in the system are not on UPS. These components could be chillers or CRAHs or fan wells or pump sets. And these components not being on UPS essentially means that the components go through a restart cycle. And in that restart, they're not able to provide the same level of cooling. And we see an increase in the chilled water temperatures that are used to cool the air in the actual data halls themselves. So by performing a simulation like this, we're able to get access to some key results, such as the chilled water temperatures at the CRAH inlets or the air handling units in the data halls, as well as other key results like the air supply temperatures leaving the CRAHs, and infer information like server inlet temperatures from that. The first step in actually performing one of these simulations is getting an accurate modeling of the piping in the system. these data halls or these data centers tend to be very large, and the volume of water in the piping is very significant in the overall system performance. So an ideal way to do this is to take an existing model of the data center. These are typically models inside of Revit. Export those models into a PCF format. Revit has some existing code built into it to facilitate this export. And then using Flownex, we can import those PCF files and convert them into piping files inside of the software for us to perform our simulations on. The next thing is to start modeling some of the key components in the system. So the first thing we'll be looking at here is a CRA model. The modeling technique for similar components like fan walls or cracks is quite similar. So for today's webinar, we'll be looking at CRAs, but it is completely possible to model those other components using the Flownex software. Firstly, at the heart of the CRA, we have an incremented fin tube heat exchanger. This is used to characterize the heat transfer performance and pressure drop inside the coil of the CRA itself. Here we capture the changing water temperature as it flows through the tubes and the changing air temperature as it flows over the fins. We then model the fan inside the CRA. Here we use a variable speed component, which allows us to capture the different pressure rise from the fan at different speeds and allows us to connect this to a control system that can change the fan speed to vary the return air temperature into the CRA. On the water side, we model the PICV or pressure independent control valves. And here we issue the valve with a valve opening or a volume flow set point. And here we then use that opening or set point to connect to another control component, which is used to control the air supply temperature. The rest of the control that you see around here is some digital control for us to use when simulating the trip of a CRA. Here we might look at what happens to the PICV during trip, if it maybe fully opens or fully closes. And it's possible to change this behavior to investigate what is going to be best for the individual configuration of these CRAs to get the best performance in a thermal ride-through event. The next area that we'll look at is the white space. So here we have two major approaches. The first is a well-mixed approach, where we assume that the temperature in the hot aisle and the cold aisle are uniform. So this essentially means that all of the cold air volume is at a single temperature and all of the hot air volume is at a single temperature. This essentially reduces the hot aisle and cold aisle into a single node. So here you can see we have these CRA components that we looked at earlier, and each of the CRAs has an inlet temperature from one hot node and an outlet to one cold node. This simplifies the system down and really speeds up solving times and is well suited to data centers with a uniform load. It does require a steady state CFD to calibrate the amount of recirculation that we see in the white space and also to calibrate the pressure drop that we see in the white space. So a small amount of CFD work is still required, but we can then use those CFD results and scale them accordingly to understand the transient performance of the system. The alternative approach is to couple the system modeling in Flownex with a full 3D CFD simulation. So here we typically use a Six Sigma room developed by Future Facilities. And in the coupling of this, we have a dedicated component in Flownex to handle the data transfer between the two software packages and give you an easy way to co-simulate between the two tools. This type of application is specifically suited to non-uniform loads. It does come with the penalty of long solving times, but as a bonus, it has fundamental calculations for recirculation in the data center, as well as the varying pressure drop with the different conditions inside the data center. So it is more accurate, but it comes with the cost of longer solving times. Looking at that well-mixed data hall model in a little bit more detail, you can see that it's made up of three major parts here in the middle. We have a pressure drop for the white space. This is the pressure drop inside of the ducting from the CRAs to the white space, and the ducting, say, from the hot aisle containment back to the CRAs, as well as some turbulence losses inside of the white space as the air is flowing around the server rack, sorry. as well as additional pressure drops in the system, such as server rack pressure drops, and then the pressure rise from the server fans. We also account for the heat input from the IT equipment here, and are able to scale the pressure drop from the server rack and the pressure rise from the server fans with different IT loads, kind of using a typical pressure drop model that we derived from some academic publications. On top of this, we also have some more models to model the other components you see in many data centers. So we have the ability to model chillers, both air-cooled and water-cooled chillers. In terms of modeling these components, it can be quite difficult to get detailed geometry of the internals of these chillers. This is not information that manufacturers freely give out to their clients. So we've developed a reduced order model that uses the steady state capacity data of the chiller and the chiller restart performance. This is information that is possible to get from chiller manufacturers and gives a comparably good accuracy for the amount of data that's required. So this gives us essentially the requirement here is essentially a commissioning test for the chiller, where we test the outlet temperature, inlet temperature, and flow rate through the evaporator of the chiller as a function of time. And this is a common test done by many chiller manufacturers and is often easy data to acquire. With this information, we require no internal geometry of the chillers and no information about the compressor inside the chiller. So it gives us a very robust transient model with information that's easy to obtain from the chiller manufacturers. Additionally, we're also able to model HDACs, or hybrid dryer coolers. These are heat exchangers that transfer heat to ambient and often use big wetted pads that cool the air before it flows over the tubes to cool the chilled water that flows through the data center. Here, that spray water that is used for cooling is modeled using an adiabatic saturation model. This is essentially the process in which the air humidity is increased and the temperature of the air decreases. This is accounted for fundamentally in Flownex using our humid air model. We connect that to an incremented fin tube heat exchanger model, and then some controllers to adjust the fan speed as well. And this gives us a dynamic model of the HDACs. All right, so that's kind of an overview of the major components we'll see in the system. Next, I'd like to move over to the Flownex software, where I can show you how this is configured, as well as show you some of the results that we can get from these simulations. So first, we're looking at a representation of the piping in the system. As I mentioned earlier, this is a PCF file that was exported from Revit and imported into Flownex. You can see each of the pipe components being modeled over here. And then in between the pipe components, I've just inserted placeholders to represent the points where we would connect CRAHs. This, I know, is a very small system. It only has 8 CRAHs per floor and 2 floors with data halls, but it's deliberately kept small to keep this demo relatively simple. For a typical data center project, we would perhaps have, say, 40 CRAHs per floor and maybe 3 or 4 floors in the entire data center. This component over here, or these pipe components, are then connected to the white spaces through what we call view nodes. These nodes are essentially connected in the piping network and are displayed on this page for us to connect the CRAHs to. So here you can see the CRAH is connected to the chilled water inlet, and then the outlet of the CRAH connects to the hot ring of the chilled water. We then connect the air side of the CRAHs to the hot and cold node that represent the hot aisle temperature and cold aisle temperature, using that well-mixed assumption that I explained earlier in today's presentation. We have our white space model in the middle, as well as the specific IT energy that we'll be using for this particular investigation. The next thing is the cooling equipment in the system. So here we're connecting our chillers again to the piping network, but now we're connecting up on the roof of the system. So these connections here are again made with these view nodes. We have a chilled water pump that sucks water from the hot ring, passes it through the evaporator of the chiller, and then passes it into the cold ring on the roof. For each of the chillers, we're modeling these as water-cooled chillers. So we have a cooling water ring here, a separate ring per chiller, and we have a cooling ring with a cooling water pump and a HDAC model to simulate the heat transfer to ambient. In terms of the control in the system, we're controlling the chilled water pumps based on the pressure in the actual hot and cold rings. So in the piping model over here, I've got these placeholders at the between the risers at each floor, and these little placeholders will measure the pressure difference at each of these locations. We then combine those pressure differences together. We take the median, it's also possible to take the average, and then pass that value into a master PID that calculates the flow set point using the pressure difference. That flow set point is then passed to a separate PID for each pump, and that PID takes the flow set point from the master PID and calculates the pump speed needed to achieve that flow. This, in essence, ensures equal flow distribution per chiller in the data center and is a very common control philosophy in many modern data centers. Additionally, on top of this, it's also possible to model the digital control logic where we would switch pumps on and off depending on the speed of the pumps. So perhaps you want to keep the pump speed close to its best efficiency point, and you might switch pumps on and off to achieve that. So using some of the digital control components in Flownex, it's possible to model that digital logic and incorporate that inside of your Flownex model as well. Okay, so next I'd like to look at how the model solves. So inside of Flownex, you can see we've constructed the model using the data center components that I explained earlier. And next we'll be looking at how the model solves and also some of the results we can obtain from the model. So Flownex itself has a transient and a steady state solver built into the same software, and we use the same components for both transient and steady state. So you don't need to build separate models for each. When you have your model set up, you can simply run the model. The software itself is using a non-iterative transient solver. This is a solver that is very efficient for transient simulation, and you can see the simulation progresses at almost the speed of real time. For a small simulation like this, we can easily obtain a real-time simulation. For larger networks, we tend to see slightly slower solving times, but typically in the order of 2 or 4 times the simulation time. So if you're investigating a thermal ride-through event, you might want to run, say, 15-minute simulation to understand what happens after the generator trip. After, say, 15 minutes or so, depending on the size of the system, you're typically going to get to steady-state conditions again. And in that 15 minutes, you would expect to run the software maybe for between 15 minutes and an hour to obtain those results. So it's possible to do quick turnarounds on different scenarios inside the system using the fast solving capability of the software. If we look at some of the key results in the system, you'll see that we can look at some results for, say, the evaporator heat transfer. Here you can see the evaporator in the beginning of the transient is running at about 300 kilowatts. For this particular scenario, I've set up an action in the software to trip the power to the chiller at 10 seconds and restore the power 20 seconds later. This essentially means between 10 seconds, after 10 seconds in the model, the chiller is not providing its full capacity in cooling, and we see the chiller capacity decrease. The reason it doesn't just decrease to 0 instantly is because of the thermal inertia in the chiller, and this is part of our characterization process in modeling those chillers. Once the chiller has restarted, we see the chiller capacity begin to rise, and this chiller capacity will increase until we're able to achieve the set point or until we hit the maximum capacity that the chiller is able to produce. On top of this, you can see a lot of other results in the system, specifically the CRA water inlet temps. So here you can see in the simulation, initially the CRA water inlet temps were 20 degrees Celsius, and now with the chiller trip, you can see the chilled water inlet temps in the system are beginning to increase quite substantially. Finally, we can look at the air supply temperatures. Here you will see with the increasing chilled water inlet temperatures, we can see increasing air supply temperatures. You see in both the air supply temps and the water inlet temps that the temperatures on the first floor are hotter than the temperature on the ground floor due to the fact that the first floor receives the hot water before the ground floor receives the hot water. So there is essentially less volume between the two locations, and therefore the hot slug of water reaches that location sooner. In terms of the control, you can see here we're looking at the CRA valve openings. You'll see that initially the simulation is running with the CRAs at about 60% open to get the 25-degree supply air temperature. But once the water inlet temperature increases, those CRA valves begin to open to try and maintain that 25-degree supply air temperature until those valves are fully open. And this essentially directly correlates with the maximum air temps that we see. Once these valves cap out, the air temperature just continues to rise because there can be no additional flow through those CRAs. We do have the ability to look at the cold aisle temps as well. And in Flownex, we do model the volume of air in the cold aisle, but as I described earlier, we make a well-mixed assumption in those white space or in the cold aisle and the hot aisle space. And this essentially gives us an average temperature for that volume. If you're looking for more detailed temperatures inside the white space, it's possible then to couple CFD software to the Flownex simulation and understand what the temperatures will be around the data center in specific locations. However, when it comes to most data center modeling work, we are typically able to take the air supply temperatures and then add a maximum recirculation amount that we obtain from a steady state CFD simulation. So perhaps from the steady state CFD, we see a 2-degree Celsius increase in the air temperature due to recirculation. So that would be 2 degrees hotter entering the server racks than coming out of the CRAs. We can simply take the maximum CRA air supply temperature, add that 2 degrees Celsius to it, and get a relatively good estimate of what the maximum server inlet temperature would be as well. So even through this well-mixed assumption, we're still able to get a good idea of what the final server inlet temperature would be with a couple of assumptions. Okay, so this simulation will continue to run until we reach steady conditions, but I've got a couple of runs already complete just so we can look at some other factors in the simulation. So first, I'm just going to load up the final results for this simulation. Here we're running with an ambient temperature of 39 degrees, and you can see on the air supply temp, we reach a maximum air supply temperature of 26.86 degrees Celsius on the first floor. If instead we had a scenario with a hotter ambient temperature, we would essentially see less cooling from our HDACs, which would result in hotter condenser temperatures on our chillers, and that will bring the maximum capacity of the chillers down considerably. With that decrease in chiller capacity, we should expect to see a higher spike on the final CRA water inlet temperatures, as well as the CRA air supply temps. So here you can see on the water inlet temperature, our maximum water inlet temp is about 25.1. If we look at the scenario with 42 degrees Celsius ambient, that increases to about 25.6, so about a half a degree increase in CRA water inlet temperature. On the air side, we see air supply temps of 27.3 at a 42 degree ambient, and when it's a bit cooler, those air supply temps are closer to about 26.8. So you can see how different ambient conditions can affect the final air supply temps, and how it's possible using a thermal ride-through simulation in Flownex to actually work out what that final air temperature is likely to be based on those different ambient conditions. We could also look at different scenarios where we have different equipment on UPS. It's often a large financial cost to put equipment such as HDACs or CRAs on UPS. So many system designers are looking to remove mechanical UPS from HDACs or CRAs and understand what impact that will have on the overall performance of the system. So using the simulation, we could also investigate how taking the CRAs off UPS would impact the overall performance of the system. All right, so that brings us to the end of today's presentation. Thank you very much for your attention today. If you do have any questions, or if you'd like to know more about our software, I'd recommend you to please go to our website, www.flownex.com. There's a page there for contact us. You can fill in a short form over there and we'll be able to get in touch with you. Alternatively, if you prefer email, you can please email sales@flownex.com, and we'd love to get in touch with you and discuss more of your specific applications where Flownex could be beneficial to your organization. On top of this, we also offer consulting services where we perform these thermal ride-through investigations or other specific data center simulations, and we'll essentially write reports that you can use in the motivation for your final data center design. All right, so that brings us to the end of today's presentation. If you do have any questions, please feel free to type them into the box on the right-hand side, and I'll get through to answering them.